let's take a look at reversible processes. So we know that entropy isn't limited to transfers across the boundaries. This means that the entropy can also be produced, and that this is how the entropy of the universe could be going up. So if we're interested in how the entropy of the system is changing, we need to consider the contribution of entropy that's transferred across the boundaries, plus any entropy that is produced in the process. It is the case that the entropy produced is always greater than or equal to 0. And this would be things like heat loss, right? So if we have a light bulb, a lot of the energy that goes into the light bulb is actually lost as heat and is not what we end up seeing as light. This entropy production term is what quantifies sort of the energy dispersal. Or sort of lost energy. This is in delta SP. And the rate of entropy production depends on how far the system is from equilibrium at any time. If the system is not very far from equilibrium, then you don't have very much energy dissipation. If the system is not at all away from equilibrium, the system is in equilibrium, then there's no entropy production, and the process is said to be reversible. So if the system is always in an equilibrium state, then delta SP is equal to 0. We have no entropy production, and this is what we call a reversible process. Now, in reality, no real process is reversible. However, it's a lot easier to sort of both learn thermodynamics and think about systems if we assume them to be reversible. So we need to sort of acknowledge that no real processes are reversible. There's always some loss, sort of in wasted heat. But we're going to assume, basically for the rest of MSE 308, we are going to assume that the process is reversible. And if you allow it to happen sort of infinitely slowly, then it's not such a bad assumption, really. So let's just look at an example, basically, of how a real process might look and how the idealized reversible process looks. So there's a difference here. So let's imagine that we have some container, and this has a piston on the top, and inside of this container there is a gas, and on top of this piston there is a bowl, and that bowl is filled up with little lead BBs, which are sort of holding the piston in place, and the force of the BBs exactly equals the force exerted by the gas, right? So in sort of one path here, we can instantaneously remove this bowl of BBs. All right, so now this is up here, and we can observe what happens to the piston. And at first, if we sort of look at the height of the piston versus time, first this piston will shoot up, and then it'll come back down, and it will sort of oscillate, and it will finally come to some resting position, so that in the final state, our system looks like this. Now, we could not just by sort of plopping the bowl back onto the piston recreate this path here exactly, right? So even if we put the bowl back on here, we can't recreate that path. So this example that I've drawn up here is irreversible. Okay, so how do we make this happen reversibly? Instead, what we do is that we keep our bowl of BBs on here, but we get a second bowl ready, and we basically take off one BB at a time, right? So we put the first one in here, and then we take the second one and the third one and so on, all the way until we've taken them all off. And in this case now, the piston gently and sort of steadily moves up to the same final height as it would have been if we'd just taken the bowl off, right? But you can imagine now if we repeated this process by putting one BB at a time back into the bowl, that we could exactly trace this path back here. And that is why we say that this particular process is reversible, because this system was never very far away from equilibrium. We moved so slowly that it essentially achieved equilibrium at each step along the way. And that's what makes it a reversible process.